Hi everyone, this is Mr. Khalil and today we will start a new lesson about lenses. It's lesson 18.2. The lesson is similar to the mirrors in lesson 17.2, the curved mirror, but there is a main difference here. In mirrors, the image is formed by reflection of light, by reflection. When we talk about lenses, so these are lenses. In lenses, the image is formed by refraction of light. So image is formed by the refraction of light. So this is the main difference between mirrors and lenses, but they are similar in cases, as we will see through this lesson. We have two types of lenses. This is called a convex lens. The convex lens is thick at the middle and thin at edges. So it is thick at middle and thin at edges. The other type is called the concave lens. The concave lens is thin at the middle. Now, the convex lens, it is a converging lens. Converging means if we have parallel rays parallel to the principal axis, the line here at the middle is called the principal or the optical axis. So the line that passes through the optical center, the center of the lens here is called the optical center. So this is called the principal axis. If a ray is parallel to the principal axis, it will go, or it will refract, not reflect, refract to the focal point as you see here. And the same thing here, parallel ray will refract to the focal point. That's the focal point here. This is convex. So the light rays parallel to the principal axis, they converge, as you see, they converge to the focal point. In the concave is diverging. Diverging means that parallel rays, parallel, of course, we are talking about the principal axis, they diverge. They are refracted away. They bend away. So the focal here is virtual. They don't go to the focal here. No focal point is here. So this is wrong. They diverge. So they appear to be going out from the focal point. As you see, this is not a real light ray. It's going out from the focal point, and this is virtual. So here F is virtual. So when we have a virtual focal point, we take it negative, or focal length. Here F is real, it is positive. Note that if we have a point the light rays are converging to this point, they will give you a real image. If the rays are diverging from the point, they will give you a virtual image. Now, if we want to draw a convex lens on a paper, we draw it this way. We draw the arrow, so that's the principal axis here. So that's a convex lens, so we draw the arrows this way. In the concave lens, we draw the arrows this way. As you see, the same shape. It's thick at the edges, this is thin at the edges. So this one has a focal length. We draw two focal points. This is the F, and here we have another F. And similar to mirrors, we have a radius of curvature, but we will not call it a radius of curvature here. It's better in lenses to call it 2F. And here we will call it 2F. So as you see, the rule number 1, parallel rays, they converge to F. Or in concave, parallel rays to the principal axis, they diverge from F. The rule number 2, a ray passing through the optical axis continue without deviation. It just continue, it just pass undeflected. The same thing applies here. If a ray is passing through, this is called the optical center. So the ray continue undeviated. So here's the same thing, we have F and 2F, and here we have F and 2F. So a ray passing, please take notes, through the optical axis, through the optical center, which is the center of the lens, it continues undeviated. It's not changing direction. Now this is a very important slide for calculation. First of all, that's a convex lens. The focal length is positive, so F is always positive. Here, F is always negative. If we are talking on the image position, which is the XI, so this is the image. XI, if it is to the left, it is virtual. Everything here or here is virtual. So that's a virtual XI. XI is negative. And if it is on the other side, which is the right side, XI is positive. So if the image is formed here, anywhere here, it is a positive image, as you see here. And if the image is formed on the left side, it's negative. The object is always on the left side, it's a positive. We take X of the object as a positive always. Now the height. The height of the image, it can be up, positive. This is for H. And down is negative. So the height of the image, up is positive, down is negative. The position of the image, left is negative, virtual, right on the other side is positive. This is opposite to the mirrors as you see. Now let's go to equations. We have two equations. The length equation 1 over f equal 1 over xi plus 1 over xo, where xi is the image position and xo is the object position. And we have the other formula, the magnification m equal negative hi over ho. Sorry, it's just hi over ho. It's equal to negative xi over xo. Now let's talk about what's the difference between real image and virtual image. The real image, it should be on the other side, so xi is positive. Every real image is inverted, so hi is negative. Since it is inverted, the magnification should be also negative. So every real image, so negative means magnification, and height negative means that it is also inverted. Now the virtual image, xi should be negative. Negative means it's on the left side of the lens, here or here. The height of the image is positive. Every virtual image should be upright, same position as the object. The magnification should be positive, just like the height. The height and the magnification, they have always the same signs since there is no negative here. So hi over ho. So if the height of the image is negative, ho is always positive. What changes here is hi. If hi is negative, so it's inverted, so the magnification is negative. If hi is positive, so the magnification is positive. Now for the magnification, if the magnification is less than 1 as absolute value, so the image will be reduced. We are talking about absolute value. If the magnification is greater than 1, so the image will be magnified or enlarged. Now, let's take a simple example. Let's say the magnification is equal to negative 0.5. What does this mean? What can we conclude of this? What does the negative mean? That it is a real inverted. So every negative is real and inverted. The 0.5, since it is less than 1, we just look at the absolute value. We don't look at the sign. If we want to know the size, it is reduced image. Let's take magnification equal, for example, 1.5. This means since it's positive, so it's virtual image. It is, since it's positive, it's upright. And of course, every upright is virtual. And it is, since it is greater than 1, it is magnified. If it is equal to 1, then it's not magnified or reduced. It's the same size as the object let's write this down. If m is equal to -1, not 1, let's take this example. Minus means that this is a real image. Also, it's inverted. Since it is 1, so it has the same size as the object. The next, we are going to go through the cases of the lenses. We have 3 cases and 2 special cases. They are easy. Please pay attention and take notes. Now we will go to case 1. I will put the object now beyond 2f. So XO is greater than 2f. So here is the object. So you have to draw 2 rays. One ray parallel. This ray will go to F. So it should be straight, this one. And we draw another ray through the optical axis here, or through the optical center. It will continue without deviation. So this is case 1. That's the image. The intersection of the 2 rays forms the image. So this is from here to here. This is XO. And this is here XI. As you see, the image here is reduced. So image it's inverted. So yeah, it's real, inverted, and it is reduced. So the magnification is negative. The absolute value of the magnification is less than 1 since it is reduced, and the image is between F and 2F. So that's case 1. Let's go to case 2. I will put the image now, or sorry, the object XO is between F and 2F. So here is the object. So that's XO. I will take the rule 1 parallel ray. The parallel ray will go to F. Another ray through the optical center. It will continue. They will meet somewhere here. You can try this at home on your copybooks and be more accurate than me. So that's the object and that's the image here. As you see, the image is enlarged and it is real. So we have, so this is the object here. So the image is real, as you see, inverted. It is magnified. The magnification here is negative. Its absolute value is greater than 1 since it is magnified, and the image is beyond 2F. Let's go. So this is case 2. You don't have to memorize case 1 and case 2. I'm doing this just to know the number of cases, not the name of the case. The third case, I will move the object closer here. I will put the object here between the focal point and the optical center. So that's XO here. So XO is between O and F. That's O here. So the same thing. I will take a parallel ray. So this is the rule. We take parallel ray and a ray through the optical center. This one will go through F. I will take another ray now through the optical. Okay, it should be more accurate. That's fine. But as you see, the rays will not intersect. That doesn't make sense. No, they intersect, but not here. Not on the real side. They intersect here. We can do this. They intersect virtually. It's not on 2F. It's not drawn to scale. So as you see, we get the image here. So that's the object is between F and. You have to memorize this and to practice them at home. So here the image is virtual. Of course, every virtual is upright and it is magnified. The magnification is positive and its absolute value is greater than 1. So this is the third case. Now we have, these are the three main cases of the convex. Of course, we are talking here about convex lenses. We have two special cases. If the object is at 2F, exactly, so XO equal to F. Let's take a parallel ray. It will go to F. And let's take a ray through the optical center. It will continue. It should be real, not virtual. As you see, here is the intersection. We also get the image XI exactly at 2F, and it is not magnified, real, inverted, and it is same size as the object. That's a special case. The magnification is exactly -1, minus its inverted 1, it's not magnified. So this is a special case. We have another special case. So special case. And here we have another special case. I will put the object at F. Let's take a parallel ray. It will go to F. Another ray through the optical, So as you see, the two rays are parallel. They don't intersect. So if the object is at F, so refracted rays are parallel. No image is formed, or you can say that the image is at infinity, since the refracted rays are parallel, so no image is formed. Now for the concave lenses, we have only one single case. It's easy to memorize. So that's a concave lens. As you see, it's thick at the edges. That's the principal axis. Let's say this is F and 2F. I will take the anywhere the object, it doesn't matter because it's one case only. So I will take the object, let's say here. So it's one case. Remember that In concave lenses, it's diverging, and F, you put it negative in the equation. So I will take a parallel ray. Remember that it diverges. So that's a diverging ray. I will take another ray through the optical center. It will continue. As you see, the rays never intersect, but they intersect virtually here. So that's the image. This is XO and this is XI. The image is always virtual, which means it's on the left side, upright, and reduced. This is the only case. So magnification is positive and it is less than 1 as absolute value.